So, what do the electron radius, the lollipop path, and the fine structure constant have in common? Well, we're going to conjecture ahead. Here we
Although
go.
this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper Rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. And while I was at the physics monastery, we were playing around. I believe we had just gone over the lollipop paths and stuff. Previous videos, you can see where I totally bait and switched Fizz to bring her to kind of to math cap. It's a good thing she brought her own sucker, else she may have been hangry. But what are we talking about? We're going to take a real quick look at the classical electron radius. Yes, this is in Wolfram Alpha. But the classical electron radius is a combination of fundamental physical quantities that define a length scale for problems involving an electron interacting with electromagnetic radiation. It links the classical electrostatic self-interaction energy of a homogeneous charge distribution to the electron's relativistic mass energy. According to modern understanding, the electron is a point particle with a point charge and no spatial extent. Attempts to model the electron as a non-point particle have been described as ill-conceived and counter-pedagogic. Nevertheless, it is useful to find a length that characterizes the electron interactions in atomic scale problems. The classical electron race is given in SI, scientific units. As RV is 1 over 4 pi, E, which E sub naught is the, was that the permittivity of free space? And they have that multiplied by the elementary charge squared. We divide that by the mass of the electron, the speed of light squared, and that gives us this number here. It's like 2.817 times 10 to the negative 15 meters. Well, that's pretty freaking small. Now, we go on in, because this is one of the interesting things. It's like, we have a calculation using SI, and it comes up with a particular measurement. However, basically, there's a couple other estimates here. We're only going to go into the Bohr radius because that's all I've really been able to really play around with. And again, they already have calculations, which are pretty cool here. But I'm just attempting to meme out there that if this is stuff that interests you, because I don't know, the first time I really started getting into math things really was like when I was doing World of Warcraft and theory crafting. It's like, how can I maximize my damage given these particular factors in this particular raid group? Do I have to be moving? Do I need to use intercast spells? Can I use my particular cooldowns in a particular method? I mean, it's just a process. That's what it is. Hashtag gamer theory. But I see you there. I'm saying, welcome, my friend. Welcome, my friend. I would love to get you to card to go. I know this really isn't your wheelhouse, but I think it's pretty freaking sweet. But we're going to jump over to the Bohr radius. The Bohr radius, some nod, is a physical constant approximately equal to the most probable distance between the nucleus and the electron in a hydrogen atom in its ground state. It is named after Niels Bohr due to its role in the Bohr model of an atom. Its value is approximately 5.29 times 10 to the negative 11 meters. Okay. So we have these, and you have that over there. 4 pi e permittivity of space, basically reduced Planck's constant squared, all divided by elementary charge times mass of the electron equals blah, 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 blah. Okay, that's cool. It's really cool. Chemistry is pretty awesome. That's basically what helps make us up. But, okay, we're going to go into our friend here, Wolfram Alpha, that being electron radius. Okay. So assuming classical, it gives us 2.817 times 10 to the negative 15 meters. Okay. We go to the Bohr radius. Okay, 5.2917 times 10 to the negative 11 meters. That's pretty cool. That's basically what we were hearing right there. And again, subject to experimental observation as well. That's important. And that's also a beautiful thing because certain models, it helps literally tighten up like a knot. Just saying, that might be a happy quinky dink. But all right, let's take those two. Let's do some basic logic. What do I mean by that? We're going to do the divisions. We're going to divide the big one because as you're doing negatives, exponents, basically things get smaller and smaller the larger the exponent because it's still a negative thing. So we're going to take, I believe that's the Bohr. Yeah. We're going to take the Bohr radius. You're going to divide it by the classical electron radius. I'm saying those words right, aren't I? Okay. But, and that gave us a number that I somewhat remembered from something. I'm like, why have I seen this 18,778 before? And apparently, when you're dealing with meters and stuff, the interpretation is stress bifringence. God, I love Wolfram Alpha. It gives you potential interpretations for all these different things. Okay, that tab's been open for a while. But, okay. So I'm like, what happens if I take the square root of this thing? You take the square root of that computation. Huh. 137.035999. That number looked familiar. Because 137 seems to come up a whole lot in physics, especially when there's a very slight deviation there. What could that be? We do 1 over the fine structure constant. Oh. Since we know the fine structure constant to a whole bunch of digits, 137 times 137.035999. Now, I'm not saying this in and of it, we already knew that the fine structure constant is heavily involved in all these different things within quantum mechanics and chemistry, ratios, the electromagnetic force, the strong force, all that jazz. I mean, we knew that, but we're going to apply the principle of the Lollipop Path. What might that be? Now, when you start looking at like the electron and stuff, so we'll just go over here. We got all these cool images here. So we'll go back, bada boom. So this is on the thumbnail here. Basically, these are some artist renditioning of basically the probability of finding an electron, because like we can calculate with extremely high probability where it's going to be, because it's technically, we think of it like a point particle, but I'm like, to me, it just kind of seems like an energy sphere from like Dragon Ball Z or Naruto, basically like a Rasengan or something. It's basically this whooshing around energy. We're like, no. When we do the observation, we end up finding it somewhere. We can calculate where it's going to be, but all these different areas, like it could be here, could be there, could be on like an outer bounds, it could be an inner bounds. All these different crazy, funky shapes, which I think are really cool. And actually, there's some great videos and stuff on, and I've shared some out before. But what might be going on here? What may potentially account for these things? Well, how about if we went to something there maybe we haven't talking about? Maybe there's been some models that maybe, just maybe, have helped to make some pretty cool predictions here. Now, again, we go over to our friend here, the Gaussian manifold. In mathematics, the Gaussian manifold is a cusp hyperbolic 3-manifold of finite volume. It's a non-orientable and has the smallest volume among non-compact hyperbolic manifolds. Same volume approximately, blah, blah, blah. Yep, cool. The Gaussian manifold has a double cover homeomorphic to the figure 8 knot complement. Oh, it's one of the primary things that used in the HF8 model. It's pretty nifty. The underlying compact manifold has a Klein-Bottle boundary, and the first homology group of the Gaussian manifold is the integers. I think that means it can go to infinity. It could be a lot of points. Unless we assume discreteness and there may be some Planckian and cutoff. Again, that's a different story. We'll get into that hopefully at some point. But figure 8 knot complement. Oh, we've been talking about this for a little while. Basically, it's a double cover, the Gaussian manifold. We're talking about Lollipop Paths and everything. It's like, okay, how might this actually be flowing? I haven't found any real good full explanation. There's like a 60-page paper by Saul Schleimer and Professor Sagerman. It's like veering triangulations there and back again. God, I love the Tolkien reference, but it's dense. I'm like 11 to 12 pages in. I'm just looking, but it's showing how potential ways to go around. And one of the things we're kind of looking to do is find a way to kind of animate this flow and just see, because I've reached out to some different folks that put on some amazing animations on YouTube. Some of the best I found involving electromagnetism. I kind of asked them what software they were using if it was possible. And they're like, well, it's proprietary software, so I can't share that. But when it comes to the answer, is it possible to model this? I got a yes. Well, that gives me hope. So what the heck am I saying? Okay. What I'm saying is, and again, just conjecture, might this whole thing with superposition, perhaps, I don't know, be because we think we're measuring a thing along kind of a sphere. But I thought within like a lot of Riemannian geometry, you had like a sphere within a sphere, a hypersphere. And then depending on what articulations, deformations, and maybe flow patterns it's going, what if you got kind of like one circle flowing into another or something? Or maybe something kind of like, I don't know, maybe our good friend here, not the big red dog, but the Clifford Taurus. Because this, if you're just going from the outside, says a property can be embedded into 2D, to R2. It's very interesting. So if you were to have something like this, maybe even perhaps kind of something, maybe like a double cover, maybe this is, because if you had the Giesecke manifold, depending on its sidedness, I don't know. We're just only trying to explain what might be going on some of the most fundamental levels of our realm of persistence. I'm not saying it's easy, but I claim it's possible. Yeah, again, I could be wrong. I'm just rampantly speculating right now. But what I'm saying is, depending on where we catch our friend over here, depending on where we're trying to measure our friend the electron, I don't know. Could it be, I don't know, maybe we're catching it on one area, maybe a classical electron race, maybe the Bohr radius. Might this explain some things? I'm not smart enough to know that, but maybe there's somebody that may watch this either now or temporally in the future that may have the ability to do it. Oh, we're bringing all the friendly sex bots in as well. It's okay. Don't spam. It's a little too much. But we could do that at some point. I do have to do some other things. I'll try to use some Discord. I'm very bad at that. I log on like once a week for like D&D. But I don't know what your background is or anything specifically with that. But yeah, we could do that. Maybe you could get on with Jen. That would be oh my god, you two clashing heads would be epic. Might be as good as when you talked with Cub. But all I'm saying is just something to ponder. Perhaps this may bring some additional perspective to a lot of folks that are working hard on this different type of stuff. But links, of course, are in the doobly-doo. I just find it interesting, again, find structure constant. Seems to come up a whole lot in a whole bunch of different things. Should probably really let folks know that we can do this, because yeah, I mean, even if everything else has to be wrong, even if just one thing is right, if the hyperbolic vortex equation just lets us actually calculate the fine structure constant, we can add even just another digit of precision into all our calculations. Wouldn't that give us better like results? Maybe get things more in line with what's actually going on if we have better measurements. Isn't that why we're talking about spending all these billions of dollars on these ginormous colliders and stuff like that? Just so we can get a little bit better. I have some big hopes with a Large Hadron Collider. Apparently, they were throwing away like 40,000 or 40,000. Like they only collected 1 out of 40,000 the amount of data, because they're getting so much data. Now they can collect a little bit more. Maybe we could get another digit or two. I think that would be pretty neat. But that's all I got for now. Peace out, everybody. Be safe. No matter what happens, we have yet to prove
The world exists on the top of a giant turtle.
Not yet, Professor. Peace out, everybody.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude. I like him.